Hello. I wanted to go over just the general mechanism of nucleophilic acyl substitution. And so first off, we have to have a nucleophile. And as we mentioned in class, every nucleophile must have a lone pair of electrons to do the attacking. And then we have to have an acyl group. That's the carbonyl group, or this carbon that's double bonded to an oxygen. And this chapter in particularly deals with the carboxylic acid derivatives, things such as acyl halides, acid anhydrides, amides, and esters. Okay, let's first start off with what happens if it's an acid catalyzed reaction. All of these go in multiple phases. Your first phase is you're going to form a tetrahedral intermediate, then you're going to get collapse of that tetrahedral intermediate. So, as the rule of thumb goes, anytime that we have an acid, that acid is going to protonate. And so what can it protonate? Is it can protonate the oxygen of the carbonyl. That's going to make the carbon even more electrophilic. Okay? And so we can have the nucleophiles, lone pair electrons, smack or crash, boom, sound effects optional, into the carbon of the carbonyl. The double bond can break, and you're going to get your formation of the tetrahedral intermediate. At the same time, this hydrogen here can be removed by the conjugate base of the acid. So I'm not even going to show that portion here. You always feel free to show that because it's reversible, but I'm just showing you the phase 1 and the product of that phase 1, which is a tetrahedral intermediate. So we still have the R, the carbon of the carbonyl, but now we have an alcohol. We have the Y group, and we have the nucleophile. So we formed a tetrahedral intermediate. For phase 2, we get the collapse of the tetrahedral intermediate. So two of the lone pair electrons from the oxygen can smack back into that carbon. And then the Y group would be the leaving group from the tetrahedral intermediate, and it can also take the hydrogen and the alcohol along with it. So the collapse of the tetrahedral intermediate is going to result once again in a carbonyl group or an acyl group being trigonal planar. So now we have the R, the acyl group, and the nucleophile has substituted for whatever the Y group was. The other product would be the protonated Y leaving group. The next portion is going to be what happens if it's base catalyzed. I should note that the extent of the reversibility of this is going to depend upon whatever you start off with. For acyl halides, which are highly reactive, they're going to proceed to the right, and they're not going to be reversible, whereas things that are more stable, such as amides, may actually favor formation to the left. Okay, except unless you go to the Shotlegger's principle, where you put in excess of one of the reactants, or you can remove a product. So in this example here, I have just a base, a general base, and what this general base is going to do is it's going to help make the nucleophile even more electrophilic. And so if this nucleophile has protonated, it can actually remove the proton. So the example that we would have here would be the base removing this hydrogen so that the nucleophile could go on and attack, breaking that double bond to form our tetrahedral intermediate once again. So it's tetrahedral. There are 4 things bound, and I'm showing the alkoxide form of the tetrahedral intermediate. Once you form the tetrahedral intermediate, you're going to get collapse of the tetrahedral intermediate, boom, and we have the Y group leaving. And I'm going to show that the Y group is taking the hydrogen back to get your base. But once again, it's going to depend upon really the pKa of the Y group in the reaction conditions on whether or not that will occur. But the important thing with respect to the acyl substitution is that we reformed our acyl group and the nucleophile has substituted for whatever the Y group was. And so that is just the general mechanism. To review is you start with your acyl derivative, you form a tetrahedral intermediate, then you get collapsed that tetrahedral intermediate to reform an acyl group, but now the nucleophile has supplanted whatever the Y group was. I hope that this helps to show or explain the general mechanism of acyl substitution using a nucleophile.